Hi folks, welcome to Unit 6, Lesson 6. So hopefully you've already taken a look at number 1 here. And we have our equation of a line, at least the standard form of the equation of a line in 2D. And I asked you to think about how we could generalize this to 3D. So it would seem that the reasonable thing to do is just to add an extra term here, add a term that's got a z. So if we wrote out, say, ax plus by plus cz equals d, that certainly looks like a reasonable generalization for this equation of a line. The question is, does this represent a line in 3D? All right. So what I asked you to do is to come up with an example and then choose 3 points and see if it creates a line or not. All right, so here, let's pick something easy. I'm going to pick x plus y plus z equals 1. Keep everything very simple. Now, because there's 3 variables in this equation, as we've done in the past in this kind of scenario, what I'm going to do is I'm going to pick values for 2 of them and then solve for the third. So I'm going to keep things really easy here. I'm going to start by picking y and z to be equal to 0. So that means x is just going to be equal to 1. So 1, 0, 0. Is a point on this object, whatever it is. So I'm going to do the same thing with x and z. I'll let those be equal to 0, and then y is going to be equal to 1. So that means that 0, 1, 0 is also a point on this object. And same thing with x and y, 0, 0. And so z is going to be equal to 1. All right? So without having to do any real work here, I can see that these are not going to be on the same line. So I do ask you here, how would you test if they're all on the same line? Well, one thing you could do is if you have 3 points, okay, if they are all on the same line, okay, you can just create vectors between them and see if those vectors are parallel, okay? Whereas if they're not on the same line, then if I take this vector and that vector, they can't be parallel to each other. But in this case here, we don't even have to do that because we see that these are just our vectors i, j, and k. Okay? Or sorry, our points that give us our vectors I, j, and k. So this is 1, 0, 0, 0, 1, 0, and 0, 0, 1, clearly not on the same line. Okay, so this is one of those cases where just the direct generalization of some object or idea in 2D, it doesn't translate into 3D. Okay, now in number 2, I asked you to think about what this type of equation might represent. So I'm going to leave this unanswered for now because I do want you to think about when we have come up to this type of equation in the past and we realize that it does not represent the equation of a line, but it represents the equation of another shape in 3D. Okay, so we'll leave that later on, and we're going to see that that's going to be a very important equation for us in the next unit. All right, so again, try to think about that. Think about where we've seen such a thing before. So if this is not going to represent the equation of a line, we need to find a way to represent a line in 3D. All right, so this is where we're going to think about an alternative to slope. All right, so let's think about what the slope actually gives us in 2D. Okay, so if I just draw myself a little picture here, a 2D plane, and I've got my line. Okay, so say I think of it in slope-intercept form, so y equals mx plus b. What does the slope tell me? Well, first of all, the sign of the slope tells me whether it's increasing or decreasing. Okay, so is this line increasing or decreasing? And then depending on the value of m, so how far it is away from 0, it tells me the steepness. Okay, whether it's increasing quickly or whether it's increasing very slowly, or decreasing quickly, decreasing very slowly. So in some ways, we can sort of think of the slope giving us an idea about the direction of the line. Okay, so let's think about how the slope tells us about the direction of the line. Okay, well, it tells us whether we're going up or whether we're going down, and depending on how steep it is, whether we're going up quickly or going up quickly or going up very, very slowly. So it gives us a sense of the direction of this line. So in order to come up with something in 3D, can we get a single number to represent the steepness or direction of a line in 3D? Okay. This is where we realize that this is going to be very difficult, okay? Because think about how we talk about the slope in 1D. It's a ratio between the increase of x and the increase of y. So if as x goes up by 2, y goes up by 1, we use the ratio of these two numbers to represent the slope or the rate of change or its steepness, increasing or decreasing behavior. All right. The problem in 3D is it's not just x and y. It's an x, y, and z. How much is this going up in the x, I guess in this direction? How much is it going up in the y? And then how much is it going up in the z? In other words, we can't represent three numbers in a single ratio. Okay. So the idea of slope is not going to work in 3D. All right. So instead, what we do is we come up with another way to represent direction. Okay, and I'll start with the 2D example, and then we're going to see in a couple of questions how we can easily generalize this to 3D. Okay, so if I take again this line, but instead of using a ratio between x and y, or the increase of x and the increase of y to represent this direction, what I'm going to do is, well, it's another thing that could represent the direction of this line. Well, how about a vector that's parallel to the line? Okay, and not surprisingly, I'm going to designate this the vector m. Okay, it does the job that the slope was doing before. All right, so this vector here is parallel to the line. Now, obviously, just knowing this vector parallel to the line is not enough information to describe this particular line, because that line is parallel to m, and that line, in fact, there's infinitely many lines that are parallel to m. So I'm going to need another piece of information. Well, similar to when we have slope. Slope is not enough to define the line, so we need a point on the line. So let's see if knowing a point on this line is going to be enough. All right. So this is the idea on how this works. The idea is that if I take this starting point, and this could be anywhere on the line, but let's say it's this one here, and I take this point and I add to that this vector. Well, where's it going to take me? It's going to take me to another point on the line. What if I add 2 times that vector? It's going to take me to another point on the line. What if I add half of that vector? It's going to take me to another point on the line. What if I add -1 times that vector? There you go. And you realize that by adding different multiples of this direction vector to this starting point, I eventually can get to any point on the line. All right? That's the general idea. Unfortunately, it's not quite a correct idea because there's no such thing as adding a point and a vector together. But what you can add is 2 vectors. So instead of thinking of this as adding to this point these vectors, is I think of the vector going from the origin to my given point. Okay, so this is what we're going to call R0. Okay, so it's a vector that joins the origin to some given point on the line. And then to that, I'm going to add some multiple of this, what we call direction vector. And when I add my given vector to a multiple of my direction vector, I'm going to get a vector to some point on the line, which I'm going to represent as the vector r. So this represents the vector to any point on the line. If I add a different multiple of m, I get to a different point. Okay? And if I add all possible multiples of this vector m, so in other words, t can take on any value in the real number system, I eventually am going to describe every single point on this line. And so what this gives us is it gives us an alternative to describing the equation of the line. Okay, so the way we write it is that we have this vector r, which represents the vector to any point on the line, okay, is equal to my vector to a given point on the line. So as we've done before, we use this R0, this subscript here, this subscript 0 to represent a specific point, or in this case here, vector to this point. So this is a vector to a known point on the line. And then we add to that some multiple of the direction vector. All right. So there we have it. And here, t can be any real number. Okay. Now the reason why we come up with this alternative way of describing the equation of a line is because this can be upgraded very easily to 3D. Okay. If I suddenly take this exact same perspective into 3D, I see that I'm going to get something very similar. Okay, which we're going to do in a second. So for now, let's just do an example. Okay, so let's go to number 4, the other page. So it says, let -3, 5 be a point on the line, and let vector 1, 4 be parallel to the line. Write the equation to represent all points on the line. Well, real simple. So here, what we're looking for is to represent any point on the line, which is going to be represented by the vector going from the origin to that point, and that's given by the vector -3, 5, my given point, plus some multiple of my direction vector 1, 4. So if I want to explicitly describe the points on the line, well, it's just going to be -3, 5 plus t times 1, 4. All right. Now, we can actually be a little more specific here. If I want to give equations to the specific components of this vector, well, what do we have? We can say that x is given by the x component of this vector here plus t times the x component of that vector there. So it's going to be -3 plus t. Okay, and the y component of this vector to a point on the line is just given by the y component 5 plus 4t. Okay, so this is what we call the vector equation, and this is what we call the parametric equation. Parametric equation. Why the parametric equation? Because we're describing each parameter individually. Okay. There's actually a third way of describing this line, which we're going to see in number 5 when we look at the 3D version. Now, one thing that you should be including here is you should be specifying that t can be any real number. Okay. Now, we're probably not going to be dealing with this too much in our course, but sometimes you might only be interested in some portion of a line, say between these 2 points here. So you would be specifying, t is an element of R, you would be specifying exactly what values of t give you that particular segment. But for our purposes, we're most likely going to be interested in the whole line. So this represents a vector equation for this line in 2D. And now what I want you to do is I want you to go through the same process as we did in number 3 and try to come up with the vector and parametric equations of a line in 3D. Okay, that's it for now.